Okay. All right, so welcome back to stellar spectroscopy. And we're going to talk now a little bit about, I think we're good to go. The Dirac atom. Shut the door. Maybe we should shut the back door too. That way we can be serious both back and front. Okay, we have the Schrodinger atom. Schrodinger gave the same energies and transition energies and therefore the same spectra for hydrogenic atoms as did Bohr. Okay, however, what could we add? We had, first of all, a whole new paradigm understanding of atomic physics, wave model, and B, remember that Bohr, his mathematics, his model, cannot speak to relative transition strengths, therefore cross sections for absorption being different from one transition to another. In his model, there was only the transition. There was nothing, no formalism by which he could say, you know, n equals 2 to 3 is more probable with a higher energy photon, blah, 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 or I should say, than a 2 to 4 transition, than a 2 to 5 transition. Why is it that H alpha is a stronger line than H beta? So that couldn't be done, but we're going to find out that Schrodinger can do that. Okay, Schrodinger and Bohr's models predicted transition energies and energy states that were slightly wrong. Okay, the precision was high enough that we could actually measure that the wavelengths of H alpha, H beta, H gamma, etc. were not exactly as predicted by the models. Also, they found out with certain metals that, etc., that sometimes lines looked diffuse in the spectra, and sometimes they looked sharp. Okay, and so, and sometimes they looked sharp but broken up into little bits. They called them fundamentals. So, Drac came along and said, let's add relativistic energies because the predicted speed or velocity of the electron was very close to the speed of light for the Bohr electron. So let's change the energy term in the Hamiltonian to add a correction to order v squared over c squared. That scared me. I guess I stepped on the cable over here. Don't want that to happen again. All right. Then he introduced spin, and so we talked about spin having a magnetic moment associated with it, and then the orbit has a moment with it, and so you had orbit and spin-orbit coupling, which was proportional to the gradient of the potential here and the rest mass of the electron. And then you had this L equals 0 angular momentum term here, which was proportional to the gradient of the potential that had to do with this jittering process where the angular momentum was interacting with the photon field transport. Okay, so when you added these terms, you got corrections to the Schrodinger model. Again, the way that we said, we had E1, E2, E3 up there. The relativistic was E1. You sandwich that portion of the operator between the wave function, its conjugate, and you get out the expectation value for that energy. And then we were able to solve all of those and write them out nicely. And we got the fractional energy for the relativistic effects, not depending upon J, only on L, therefore causing a shift in the energy levels due to the relativistic motion of the electron. Then we had the spin-orbit coupling. There was a term that you get if it was J equals L minus a half. There was a term that you get if it was J equals L plus a half. In other words, whether you were spin up or spin down. Okay, and they depended upon J. So now we see that the fractional energy change due to spin-orbit coupling involves splittings at different n levels because there's a J dependence as well. And then you have the Darwin Effect, which is basically the fractional energy being proportional to the fine structure constant squared, and only affects L equals 0 terms. The full fractional energy change, okay, was given by this term right here. And it turns out that this is the term that the people used to try and understand how the fine structure constant alpha evolved with cosmology, because notice that this fractional energy change is proportional to alpha squared. So they're able to measure the spectra and see if things are as predicted by Dirac with a function of cosmic time. If they're not predicted as Dirac said, and that changes with cosmic time, the thought was that this is what's evolving with cosmic time. It's a little bit of an aside. Okay. And I showed you the full-on expression. E equals nj now. So for every n, there are a number of j's that are allowed, and then you get different energies for each j for a fixed n. Okay. So this is the part that I want to review for you. Let's say these are the Bohr-Schrodinger energies, okay, carried through here dot-wise. Here are the fractional energy shifts in units of 10 to the minus 6, so parts per million. So this is very small shifts and splittings, yet small enough that the spectrum predicted by Schrodinger and Bohr was wrong to experimental accuracy and precision, and why diffuse lines in low resolution spectra and why double splittings in high resolution spectra. N equals 1, you can only have L equals 0, okay? But you can also only have, if you remember right, J equals a half. So remember that J was equal to a half when L equaled 0, and equal to L plus or minus a half when L was greater than 0. Okay. So L equals 0, J equals a half. Your spectroscopic notation now becomes NLJ, where L is now, remember, L equals 0 is S, L equals 1 is P, L equals 2 is D, and L equals 3 is F. Okay. Minus 13 parts per million is the energy shift downward. So the ground state of the electron now is 13 parts per million more bounded in Dirac's atom when you account for relativity than it was in the Schrodinger model. More bound. The N equals 2. N equals 2, you can have L equals 0 or L equals 1. When L equals 0, J is a half, okay? L equals 0, J is a half. So you get the 2s 1/2 state. It's shifted down 5 parts per million, okay? Well, from here it is, total of 8. Then when you have J equals 1, you can have minus a half, so J equals a half. So here's the 2p, where L equals 1/2, okay? Has the same energy as the 2s 1/2, because what does the energy depend on? N and J. So 2ps 1/2, 2s 1/2, same energy. L equals plus a half, that would be 3/2. So here's your 2p for L equals 1, 3/2, 1 3/2, and it only is shifted down by minus 3.3 parts per million. Again, it is a separate energy because N equals 2, J equals 3/2 is on state. So you have two states. They're both shifted down different degrees. Now, when you have a transition from N equals 1 to 2, you can have this transition or you can have that transition. That is called a doublet. And that's called fine structure splitting or fine structure doublets. N equals 3, okay? Well, N equals 3, L can equal 0, 1, or 2. When L equals 0, what is it? J is a half. So S is a half, here it is, minus 13 parts per million, okay? When L equals 1, minus a half gives you a half for J. Again, it has the same energy because it depends upon N equals 3 and J equals a half. Same energy, boom. And then your when L equals 2, you have 3 halves and 5 halves. So here's the L equals 1, 3 halves. Here's the L equals 1, L equals 1 half, 3 halves, and then, when L equals 2, it's 3 halves, 5 halves. So here's L equals 2, 3 halves. Same energy as L equals 2, 3 halves. Okay, and then the L equals 2, 5 halves, which is only shifted about 1.5 parts per million. So now you can actually have 1, 2, 3, 4, 5, 6 different variations. Okay. Did I count those right? Yeah, I think so. Okay. So the atom has become much more complicated now. All the electrons are slightly a bit more bound, but you have this splitting. The energy depends upon only 2 quantum numbers, N and J. In Dirac's model, if you have the same N and J, you have the same energy, no matter what your L is, as long as J is plus or minus a half of L. Let's look at the selection rules. Okay. Remember the Schrodinger model. Okay. You had delta L plus or minus 1, so you could do that, you could do that, you could do that, you could do that, you could do that. I think I got them all. Well, you can do the same thing with the Drac model, but you also have delta J is 0 plus or minus 1. Okay, so if you remember right, now I'm going to add in what the Dirac model looks like. First of all, this is down a little bit, okay? This is down a little bit, and this is down a little bit, but there's also another one, okay? This is J equals a half, J equals 3 halves, J equals a half, J equals a half, okay? You allow that I don't have to split these down, okay? Let's see if I get this right. Half, half, 3 halves, 3 halves, 5 halves. Okay, everybody with me? L equals 0, N equals 1, L equals 0, it's a half. L equals 0, it's a half. L equals 0, it's a half. J is a half. Okay? L equals 1, 1 minus a half is a half. 1 plus a half is 3 halves. The energy for 3 halves is slightly above that of the 1 half. Okay? L equals 2 minus a half is 3 halves, has the same energy as the 3 halves because it depends on J, and energy for 5 halves is up here. Okay? Now let's look at the transitions. L equals plus or minus 1, but J has to equal 0 or plus or minus 1. Okay. First of all, J can equal 0 plus or minus 1. Can I do 2p 1/2 to 1s 1/2? What's delta J?
0.
Is that allowed? Okay. What's delta L?
1.
Minus 1.
Minus 1.
Just to get you. Minus 1. It's allowed. Yeah, it's allowed. Okay. All right, let's go here. What's L? Feed me. What's L?
0.
What's J?
1/2.
All right. What's L?
0.
Can we do it?
Nope.
Nope. What's L?
1,
What's J?
3 halves.
Okay, what's L?
0.
Okay, that's 1 to 0. We're good. What's J? 3 halves. J's 1/2. What's delta J? Is it allowed?
Yep.
Hot dog. Doing my George Bailey for you. Now don't tell me that I dated myself and you don't know who George Bailey is. Who doesn't know who George Bailey is? Oh God, I'm old. Google him. It's an old Christmas classic movie called It's a Wonderful Life. Donna Reed. Okay. George Bailey. And he always goes around when he's happy going, hot dog. All right, sorry. Okay. All right. Lest we digress. Can I go from here to here? If you're going to say yes, you're going to tell me why.
Where to where?
Can I go from here to here?
Yes.
Why?
L's
sorry.
changing by 1.
It is
L,
allowed.
It is allowed. Why is it allowed?
Because it.
L.
Delta J is 0 and delta L is 1.
Thank you. Is this allowed?
Yeah.
Because,
Delta J is 1 and delta L.
okay. Now you guys are giving me the absolute magnitudes, but if you really want to be precise, you have to tell me whether it's +1 or -1, right? Don't mess with me. I want
It would be
the
1,
sign.
right? If you're going from L to 0.
Sorry?
Or from 1, if you're going from L equals 1 to L equals 0, it's
-1. L's
it's not
minus
1
1.
minus 0, it's 0 minus 1.
It's 1 minus 0. Yes, but you went from, it's not a subtraction problem. You went from L equals 1 to 0, so the change is -1.
Okay.
Gotcha. I could see it now. It's like sort of like, this is going to mess me up. Right? Well, it's messed me up too. Imagine trying to write a book and do this stuff where you got L primes and L's, and is it changing -1 or +1? Let me tell you, it took me a whole summer to write these 4 chapters. And I mean 12 hours a day. I lived here. I know I don't live here anymore, but I lived here then. Okay, let's do some more. Can I go from here to here? From here to here.
No.
Why?
L's the same.
L doesn't change, okay? Can I go from here to here? I can't hear you.
Yeah.
Yes. While I'm drawing it, tell me why.
Because you can.
L is -1.
Because God said so. No, wait, because Dirac said so. Let's tone it down here a little bit. All right. Delta J is allowed for 0, delta L is 1. Okay, boom, -1. That's allowed. Delta J is 1. I'll just give absolutes, and delta L is 1, because I'm giving you deltas. All right, now, okay, can I go from here to here?
Yeah.
Okay, can I go from here to here?
Yep.
Yes, I can. Can I go, oh boy, here we go. Can I go from here to here?
No.
There's 2 reasons. 2 to 0, and 3 halves to 1/2. Actually, I'm wrong. You could do that, but ruled out by the selection rule. How about here to here?
Yeah.
Yeah. How about here to here?
Yep.
Because delta J is 0. All right, how about here to here?
No.
Why?
Too much J.
Too much delta J. I like it. And here to here?
Yeah.
Yes. Did we get them all? I think we got them all. Great Kuhn question. Oh, even better class orals question. Okay. It's a lot different than Schrodinger, isn't it now? And the energy, even though this is n equals 3 to n equals 2, the energy of this one to this one is different than the energy to that one, so you're going to get a different energy photon in the spectrum. However, there are degeneracies. let's say, for example, this one here to this one, which is n equals 3j equals 3 halves to 2 1/2, 3 3/2 to 1 1/2. This one here is degenerate with that one there. Right. This one, there's no degeneracy with any of them. This one is degenerate with, whoops. Trying to find the other degenerate one. Help me out here. I think it's this one and this one. 1/2, 1/2, 2, 1/2, 1/2. Yep. Because it depends upon the J. So those are energy degenerate.
Because they're going to the same J state?
Because they go to the same J state.
That's the only
Well, they start at the same J state and end at the same J state, so they're in J's. Their J's don't change. Their starting J's and ending J's are the same, even though N changes. So therefore, the difference, the energy difference from top to bottom, is the same for both of them. Because look,
But and they have to be in the same.
start energy here, end energy there. Okay. Start energy, same. End energy, same. So the delta is the same. They're the same wavelength photon. Any more? Then hiding in here is the fact that you have all these delta, different M states and different spin states. The other thing that is not allowed is the spin cannot change. Starts at spin up, goes down to spin up. Okay.
What
This
about
is-
hyperfine transitions then?
Hyperfine transition is a forbidden transition. So the probability, these are, I'm glad you asked that, these are what are called dipole selection rules. I haven't explained to you what a dipole selection rule is yet. But there's also quadrupole selection rules. Dipole selection rules are what are the rules that we adopt as being allowed transitions. These are the ones that have the highest probabilities of happening. When you get to the higher moment of the electric field moments of the upper and lower wave functions, because remember they each have a electron density distribution, and you look at the moments of those, you have dipole moments and you have quadrupole moments. Okay? The ones that have no dipole moment but only have a quadrupole moment, those transitions can happen, but they're only very improbable. So they're called forbidden transitions. Okay? So in the formalism of this, what we say is, and there's also magnetic pole moment, dipole, and magnetic quadrupole that you can get into. And so the fine structure transition is one of these higher moments. It can happen, but it's much lower probability. Okay? Therefore, if you have an electron that's in a certain spin state, and it can become metastable. Because why? Basically, what is that? It's a fine structure state down here that hasn't yet been delineated to you. So I better not get into it, fine structure. I actually have written some chapter pages on fine structure, but I took them out of my book because I'm doing atomic spectroscopy, not radio. But if you want that chapter, if you're going to do radio, I'm happy to hand them to you. All right. But anyway, there's something called parity, and this violates something called parity. And then the delta M sub j can be 0 plus or minus 1. And notice that the energies don't have an M sub j in them. There's no, in the equations, you don't see any M sub j. Therefore, they're energy degenerate with M sub j as well. You basically look at the equation. What does it have in it? N and J. doesn't have an L. Well, the one has an L, but you can write L in terms of J. And then you don't have any. Okay. So these are the Lyman doublets. N sub P 1/2 to 1s 1/2. Okay. This is the 1s 1/2 state. Make n equals 2. You have the n equals 2p 1/2 to the 1s 1/2. Or you have the 2p 3/2. That's this state to the 1. So basically your series now can be written like this, where n is n, and n can change from 2, 1/2, 3/2, or 3, 1/2, 3/2, all going down to this state. So all Lyman series lines can now be written like this, and notice that they're all doublets. Why? Because in this P column, the fine structure is always a doublet. Okay, so you have 1, 2, 1, 2, and they're always 1/2, 3/2, 1/2, 3/2, and those are all allowed from the selection rules. So you get Lyman alpha, Lyman beta, up at n equals 4, Lyman gamma, and you get both members of the doublet. The one that comes from the 3/2 state is a photon, which has a slightly higher energy than the 1/2 to 1/2. So they come as pairs. The one that's at the bluer wavelength is always from the 3/2 J state. The one that's at the redder wavelength is always from the J equals 1/2 state, and the upper state. Okay, it's like English. That's the rule of thumb. But there can be exceptions. But for hydrogenic atoms, okay? So when I look at my magnesium 2 doublet in my absorption lines, like this is 2796.352. This is 2803.521 angstroms. This is the 3p 3/2, and this is the 3p 1/2 going down to the 2s 1/2, 2s 1/2. The 3/2 is always the bluer wavelength with the higher, lower wavelength, bluer, higher energy. If you were to see a Lyman alpha line split in two, okay, the bluer one is the one that's coming from the upper state, obviously. So here is the growth train diagram with the actual energies written in here, okay. So basically, this is a very precise drawing of this slop on the board. See, I told you I was going to try and mix it up a little bit more now. Okay, hope it's helpful. Right. This is the excitation energy, the ground state here at 0, n equals 1. Now remember, this is for hydrogen or hydrogenic atoms. They only have one electron. Okay, later on, when we have multiple electrons, n equals 1 is not always going to be the ground state. So think about that. All right, here's your Lyman alpha. Okay, n equals 2. For J equals 1/2, L equals 0 and 1, it's 10.19 is the excitation energy. For the J equals 3/2, it's 10.198992 versus the 10.198947. Okay, so it tells you it's only a slight energy difference in electron volts. Okay. Here is the binding energy now, down here at 13.598611. Here are the binding energies of the electron if it happens to be in one of these other states. Go up to n equals 3, or all the way up at 12.0876 and some change. Okay, J equals 1/2, 5.4, J equals 3/2, 6.7, J equals 5.5, 7.1. Here's the binding energy. Okay, And then you can see the transitions that are available here, okay, because of the selection rules. And you can see that I've used the spectroscopic notation, 2p 1/2 to 1s 1/2. This is 2p 1/2, 3/2, sorry, that's a 3 halves. That's a 3/2. I can't read it from here. So this is the 2p 3/2 to the 1s 1/2. This is the 2p 1/2 to the 1s 1/2. And so now when you see that notation in a book or particularly in a paper, and you actually, some people write that stuff in their papers, you'll know what they're talking about now. That subscript means the J state. The letter S, P, D, F means the L state, and the number in front is the N state. And now, ladies and gentlemen, you understand or are beginning to understand the formalism of fine structure that you will see in the literature. Yes?
The drawing on the board, is that supposed to be 2p to 1s?
This one?
Yeah.
This is for magnesium too.
Oh, magnesium.
Yeah, so it's different. It actually, yeah. Actually, this might be a 4 and a 3, I can't remember. But it doesn't matter. It's an example. It doesn't have to be a self-consistent example. Well, parts of it don't have to be self-consistent. Other parts have to be. All right. This is what Drac came up with. Are there any, I'd like to discuss it if there are any questions. It's a lot of information, and you can't understand the spectroscopy of multi-electron atoms if you don't first have some feeling or notion of what's going on with the Dirac atom for hydrogenic atoms. I don't see any questions. Okay, so I can throw all kinds of these things at you, and you can look at them now and go, allowed, not allowed, allowed, not allowed, right? You just have to look at the J's. Does it change by 1 or 0? Yes. Look at the S's or the P's or the D's. Do they change by 1 or 0? Yes or no? Done. There is no rule about delta N, is there? No. You can't have a delta N in the Schrodinger model because all the levels at level N are degenerate. But in Dirac, that's not the case.
N has to change by at least 1, right?
It does not. Is this allowed? Unless you have N has to change by 1, it's allowed. Okay? And it turns out that that transition allowed us to get even more information on the atom and its spectrum and realize that, guess what, Dirac didn't have it 100% right. That's our next stage. That transition has a special name. It's sometimes called the Lamb transition. And it has a predicted energy in the Dirac model. And we're going to find out that it's not necessarily true. Yeah. Here's the deal. Let's go back to this, Emma. I was wrong. This isn't exactly the Lamb transition. What we're going to find out is that, well, is this transition allowed? The answer would be yes, except for that these have the same energy, so it doesn't matter, right? It's like, that's the same question as in the Schrodinger model. You can't have a delta L with no delta N. There's no energy change. In the Drac model, there's no energy change. Okay. People found out later was that, in fact, there is a transition from here to here because Drac's energies are just a little bit wrong. And in the Drac model, though the energy only depends on N and J, in the real world model, the J's can be a little offset. And you're like, oh God, would you slow down? I just got used to Dirac's model. Now you're going to tell me that he's wrong. Sorry, he's wrong. Okay. it took Richard Feynman in quantum electrodynamics to quantize the electromagnetic field and add that in. And once you quantize the electromagnetic field, you realize there's virtual particles swimming around inside of the atomic space. And the presence of those virtual particles shifts the energy content of that space around the atom, causes some of the energies to shift. Virtual particles popping in and out of existence, called vacuum polarization. Okay, I know. You lost me, Chris. Can we just quit and go home right now? Okay. Yes?
So, like, what kind of photon would we expect to see from a 2s 1/2 to a 2p?
It's out in the
1/2?
radio at around 10 or 1,000 megahertz or something like that. 1077 megahertz or something like that.
So, like, barely a photon at all at that point.
Well, it's a photon. It's just in the radio. Well, come on. I mean, you pick up photons in your at 107 megahertz in your radio dial. Those are bona fide photons.
Hey Chris,
Yes.
so even if the energies were exactly the same between,
Right. And in the Drac model, they are.
right,
You know, it just depends on what model you're talking about.
yeah, so
Yeah.
so like in real life you're saying that they are slightly different.
Right. And that's
So-
that's what we're going to talk about next.
Okay, so even if they were the same, why would the electrons still not be able to transition between the two?
That's an excellent question. I would say that it does. If this was reality, I would say that there is no physics to go to zero probability of that transition. What would happen is that would be an internal adjustment of the atom in which there would not be an emission of energy. Since the atomic system did not change energy, there would be no energy coming in or coming out that
Right.
would be involved in that.
Okay.
Right, exactly.
But then it could still happen, or no, not really.
I think theoretically the answer is yes, because when you get into the formalism of how transitions happen, which involves doing these things called overlap integrals of the wave functions, is the only things that are truly not allowed is when you do this integral and the answer comes out to be 0. In the case of doing this, you probably would not get a 0. Okay. I have not looked at what the answer to that overlap integral is. My guess is it probably can happen. It's possible that if one sat down or looked it up somewhere that it might be 0. I don't know the answer. But in principle, just saying if that wasn't 0 and it was allowed, and my guess is from the things that I have learned is that I think it might be allowed. Again, it would be a change of energy internal. No, there would be no internal change of energy in the Dirac atom. Okay, but it turns out Drac didn't get it all right. I hope I answered that satisfactorily.
Yes, yeah.
Okay.
That seems like it would violate entropy or something really basic.
Now I just don't speak that language.
Yeah.
What's going on with entropy?
I don't know. It seems like that shouldn't be allowed.
I'm jesting. But I don't know. Is the atom more organized if the electron or the singly? I mean, you have to think about it. This is a proton or a series of protons and neutrons with one electron. Does it change the entropy of the atom if it's in the L = 0 state versus the energy hasn't changed? What's entropy? It's delta Q over T. Has the heat, has there been a change in the heat, delta Q? No. So I don't think it changes the entropy. That's my guess. I'm not a physicist. I'm an astronomer. Okay. I have to always have a disclaimer in case I'm wrong, especially being on film. And then I put myself on YouTube. I'm really taking risks. Let's look at the Balmer multiplets. This is H alpha. H alpha has 1, 2, 3, 4, 5, 6, 7 transitions to it. What? H alpha is a single line in the spectrum. What are you talking about, Chris? Drac says no. There are 7 different ways to make H alpha photons, and they don't all have the same energy. And here they are. Here are 5 of them. 1, 2, 3, 4, 5. And here are 6 and 7. 6 and 7 are degenerate with 1 and 2. Okay, so these are the 2 circles and these are the 2 X's. Or vice versa without looking at it closely. Yeah, these are the 2 circles and these are the 2 X's on that diagram. Okay. This is interesting. This means if you had a super high resolution spectrograph, you should see 5 individual spectral features from on H alpha for an H alpha 1. And what you're really measuring in a spectrum when you measure the H alpha is the combination of all of those blurred together. No longer the Bohr model, no longer the Schrodinger model, the Drac model. H alpha, 5 unique photons blurred together. They each have different relative strengths, actually. Some of these transitions are more probable than others, have higher cross sections, therefore have higher intensities. They don't all have the same relative intensity. All right, now we get into the fact that people made some measurements that said, guess what? Dirac's not 100% on the money here. Let's go to the next step. They're called radiative corrections. Okay. Remember before we? Yes, ma'am.
Sorry, I have a quick question.
Yes.
So degeneracy, those lines are degenerate, and they have the exact same energies, or is it slightly different?
They have this one and this one.
Are the exact same?
They give you this exact same energy photon, whether it's absorption, or emission, and these two give you the same exact energy. So that's why we say they're energy degenerate. So you have a multiplet, but it turns out there's also some degeneracy in these. In the Dirac model, those are degenerate in the Dirac model because the Dirac model, the same J state has the same energy, no matter what its L state is. Okay. We're going to find out that's not true when Richard Feynman gets involved. One of the reasons he got a Nobel Prize. Okay, you remember that it was the Stern-Gerlach experiment that gave us electron spin, from which we then were able to add spin and get the energy splittings from the L dot S, the spin-orbit coupling. Okay. Well, likewise, it turned out that delta N transitions are allowed. Okay, and in 1947, okay, Lamb and Rutherford wanted to see if you could get a transition from the 2s1 half to the 2p1 half. 2s1 half, 2p1 half. In the Dirac model, we were just talking about it, those are the exact same energies. So you're not going to have a photon come in and knock an electron from here to here, or a photon released and knock an electron from there to there. It's not going to happen in Dirac. Okay. They measured, okay, a photon coming out with identical N and J states coming out around 1,000 megahertz. Okay. And it corresponds to an energy about 10 to the minus 6 eV, a frequency, or a wavelength of about 28.34 centimeters. And the exact wave frequency is 1057.77. I said 1077. I knew there was a 77 in there somewhere. This is called the Lamb shift, okay? And basically what they're saying is this 2p 1/2 energy level is actually shifted relative to the Drac model. That shift they call the Lamb shift, okay? Now, why does it happen? Have you ever seen a Feynman diagram before? I'm getting a yes. It's basically space versus time, and there are certain rules. Okay. This is space. This is time. An electron not changing location travels through time in a straight line. An electron at rest. Okay? An electron moving through space travels through time and space and covers a curve like that. Okay? Constant speed. Okay. Now, let's consider an electron moving through space and a photon moving through space, and we say that they collide or interact. Then, without moving through space, but only time, we have a virtual electron, which then the real electron continues on deflected, and the photon continues on deflected. Anything where you have a line connected by two vertices, that's a virtual particle. So basically what Feynman is saying is scattering process is a real electron hitting a real photon, but then there's this time period where there's a virtual electron there while it decides to transfer the momentum and energies and all those things and conserve all these properties like lepton number and spin and angular momentum, and then the electron is deflected but off of the photon, and the photon is deflected off of the electron.
So it slows down the photon during that time because it's not moving?
No, it's just a period of time, and this period of time is defined. This period of time is defined by the Heisenberg uncertainty principle. So the summed energy of the electron and the photon come in. This virtual particle will have the sum energy of those. Okay, that if you take, I believe, h bar over that energy, you get the delta t of the virtual particle, where this energy is the rest mass energy, or center of mass energy, kinetic plus rest mass of the incoming particles. Obviously, this time period is very short. Okay.
So it's sort of just like a time period in which.
Yeah, it's and you're borrowing energy from other things, but you have to give it back before Heisenberg sees it. Gosh, it's so funny. My wife, I was telling her about how you sandwich the operator between the wave functions to get out the expectation values. She goes, "Is that how Schrodinger got his cat?" I thought it was hilarious. I said, she actually finished the sentence for me. I said, "You sandwich the operator between the wave functions," and she goes, "And you get Schrodinger's cat." I just thought it was hilarious. Sorry, my inside joke. Okay, everybody follow that a little bit now. Now, that's what's called a zeroth order interaction. The virtual particle in that quantum borrowed time is the lowest order thing that can happen. You also can have two electrons coming at each other. Here's electron 1 coming to electron 2 through the electromagnetic force, okay, which the carrier is a virtual photon. A virtual photon is almost instantaneously transmitted from electron 1 to electron 2. Notice that this is tilted a little bit because it's moving very fast at the speed of light. Okay. When this virtual photon leaves this electron, that electron is deflected. When this virtual photon interacts with that, it scatters that electron. Okay. Now remember, this is a real photon scattering. This is a virtual photon. Okay. it exists in a time of delta t, which is 2 times mc squared divided into h bar. Okay. So this is how Feynman describes the deflection of electrons. So, you know, when you tell your 110 students like charges repel each other, this is the way Feynman would say it. Okay? Virtual photon is transmitted in a very short period of time between these two particles. Okay? This also is a 0th order interaction. But let's now ramp it up. This is where I lose everybody, or I lose most of the students. Same interaction. Okay? This photon has some energy, which is equal to basically 2 mc squared. Okay? And so it has a period of time that it travels through, h bar over 2 mc squared. But what's to say that while that virtual particle is existing, that it has to stay in the form of a photon? Right? Virtual particles, you're just basically transferring energy forms and mass forms equals mc squared back and forth. It doesn't matter. It's a big dance. As long as it all happens within delta t, we don't really know what's going on in there, do we? But in principle, why not? Your virtual photon transmit itself into an electron and a positron. Everything's conserved. What's the charge on the photon? 0. What's the net charge of a positron and a proton, or positron and electron? Just someone talk to me, please.
0.
Thank you. 0. Okay. What's the lepton number of a photon? I'm going to test you on this one. 0. What's the lepton number of an electron?
0.
1. What's the lepton number of a positron? -1. What's the total net lepton number of the particle-antiparticle while it's in virtual purgatory?
0.
Okay, energy is conserved because whatever the energy of that was, you're back to having the same energy. Lepton number conserved, charge is conserved. You want to get into a whole list. Strangeness is concerned, charm is concerned, baryon number is concerned, but we don't have to worry about those. Anyway, the photon, then they come together through their mutual attraction and annihilate one another and turn into another photon, still in virtual purgatory. Then that virtual photon hits our other companion, real electron, and deflects it. Yeah, in principle, is there any reason that can't happen?
Why would it happen?
Yeah, in principle, is
Why?
there a reason that should happen?
Let me just go a little further. Why is there a universe with existence in it, and we're here to talk about it? And let's just get it. Let's avoid the n to the -1 factorial questions and get to the bottom line. If it can happen in the universe, it probably does somewhere. That's my rule of thumb. Okay. Now, sorry, I don't mean to belittle your question. Now, if there was no physical ramification of detectability of this process, then your question is, we're not going to talk about it because we can't talk about it, right? It's your Y on steroids, right? But guess what? We can discern it. Yes, sir.
When a positron and a electron collide, doesn't that make 2 photons, or am I completely wrong?
Maybe it only makes half of each.
I have heard that. I believe that is correct because of angular momentum. believe that's correct. So I cannot address that when it comes to the virtual world. But I would imagine the angular momentum has to be conserved. But then again, we're talking about the virtual world where things are borrowed and put back before we see them. So that's a damn good question. Somebody should Google that and come back to class and say, hey, does a virtual positron create two virtual electrons or vice versa? Damn it, I need to know.
Could it be two lower energy virtual photons come out of that?
Yeah, it could be, but
Like you
then,
start out
but
with
then
a
both
higher
of them,
energy virtual photon, it splits and then it comes back as two.
there must be something about the conservation. For example, perhaps the presence of this electron here affects the angular momentum in purgatory virtual land, such that this process can happen. Now, the thing is that that's how you can absorb a photon by a free electron, for example. Free electron cannot absorb a photon. It's going to scatter. But if you have an atom nearby that can absorb the angular momentum, even though the energy state of the atom won't change otherwise, you can get the angular momentum transferred to the atom, and the photon, or the electron, can absorb the photon. It's called a free-free transition. So something like that could be taking place here. I say we all march over to the physics department right now, walk into the department head's office and say, when a virtual positron and electron annihilate, doesn't it create two virtual electrons? Okay. Good question. Glad to see you guys thinking. Okay. This can go on for infinity. You could actually have virtual photons come off. This would lose a little energy. You have virtual photons come off. You can have, if you go look at Feynman diagrams and you look and you see, you can do infinite possibilities as long as you conserve all these quantum numbers and each slice of time and space at any event time space point, then all possibilities are possible. Okay? As long as you're not borrowing more energy than you started with, all right, and it doesn't last longer than the total E that you started with over 8 and divided into h bar, any combination of virtual particles coming in and out and photons coming in and out and doing their thing is possible. I've seen diagrams where another photon comes out here, another positron pair annihilates over here, the photon comes back and bonds with the photon there. Okay, and this is what they called the normalization problem, because when they started doing the integrals of all these possibilities, they couldn't get their integrals to converge. And they had to come up with something, maybe you've heard of it in physics, called renormalization, which is beyond the scope of the class. Translation, don't ask me how you do it. I don't know. Okay. But let's just go with the first order positron-electron virtual pair. Well, it turns out that this creates a small electrical polarization in space. And even though it's happening in less than delta t, it does create a small discernible polarization in the electric potential. Okay. If you're talking about the electron going around the proton and there's two electrons interacting with each other or whatnot, then you have more of a net positive charge in this part of space and more of a negative charge going on. Because this is going on trillions, gazillions, of billions of times per second in this, electron going around, giving you the old Bohr model, gosh. Some probability distribution, electron fuzz. Okay, there's the virtual photon the virtual photons that are continually communicating between the nucleus and the electron are constantly creating little positron-electron pairs. Okay, polarizing the space electrically and changing therefore the gradient of the electromagnetic potential between the electron and the proton. Whoops. Was that kind of like a drum roll? Did that make sense? So, you know, you're used to the regular curve of the electromagnetic potential. I guess it goes like this. All right. What we're saying is that curve slightly gets adjusted because of these virtual pairs of positrons and electrons. The virtual electrons naturally are gravitated toward the nucleus because it's positive charge, and the virtual electrons, positrons, are naturally gravitated on when they're created to go toward where the electron cloud is, and you end up polarizing the space and changing the gradient of the electromagnetic potential.
Yes. Are we able to talk about the probability of a B versus C on a diagram occurring?
I believe,
Is that
yes. I believe if you went to the full quantum electrodynamics, that probability, the formalism for calculating the probabilities exists. Yes. All right, so I just wanted to introduce to you this idea, and it's called vacuum polarization. It has to do with virtual particles, and if, to answer your question why, if we made this up in our minds, but it didn't change anything about the potential in the atom, then we wouldn't talk about it anymore. But in fact, this is Feynman's picture of what's happening, and it explains when you add it into the physics of the atom, it shifts that 2p1/2 state slightly. Therefore, you get the 28.43 whatever centimeter photon for the transition of 2p1/2, 1s1/2. That wouldn't happen if you couldn't include some physics to make it happen. This is the physics we believe is happening. Not that you need to know it, but this is some of the equations which describe it. You don't need to know that stuff. I just include them. The point is that they're on the order of alpha cubed. All the fine structure changes were on the order of alpha squared. This is an effect which shifts energies, doesn't split them, but shifts energies on the order of alpha cubed. Okay? Alpha cubed over n. So as you go to higher n, the fractional energy shift that you get gets smaller and smaller and smaller, and whereas before they were on the order of alpha squared, they are now on the order of alpha cubed, which is even smaller. That's the point. And ladies and gentlemen, here's what you get. Everybody see that? Here's the non-relativistic Bohr-Schrodinger energies again, all degenerate for level n. I bet you guys have no idea that the hydrogenic atom is so complicated, right? Which makes me feel good. If you're learning something, I'm happy. Here are the shifts due to the Drac model. Shift to the 1s state, 1s half. Here is the 2s1/2, 2p1/2. Here is the 2p3 halves. Here's the 2s1/2, 3p1/2, and the 3p3 halves, 3d3 halves, and the 3p5 halves. Okay, we've talked about those shifts and splittings in the previous model, and to which we got our Grotrian diagram and our transitions. Now, look at this. Of order alpha cubed, which means it's actually really small, this is exaggerated, the ground state electron is actually a little bit less bound. Okay. What happens here? Oh, degeneracy is broken between 2p1/2 and 2s1/2. In fact, I lied, it's not just one that shifts, they both shift. 2s1/2 shifts up. This is the energy transition of the Lamb shift photon. 1054.77 megahertz or whatever it was, I can't remember. This is the Lamb shift. Now, if you look at the handwritten notes, I wrote the wrong one. So you might want to fix your handwritten notes. I think I wrote it between here and here somewhere. No, it's these two right here. That's the one that was being measured by Lamb, and it's called the Lamb shift. The physics of radiative corrections is called the Lamb shift. In this case, we have a small shifting with 2p3 halves, more bound. 2s 1/2, 3p 1/2, 2p 1/2 down, 2s 1/2 up, and then again the splitting of the 3p and 3d 1/2, 3 halves, boom, a boom, and then a shift upward slightly of the 3p 5 halves relative to Dirac. Okay, that, ladies and gentlemen, will end our discussion of how you get fine structure, and finally, after Richard Feynman quantum electrodynamics, you actually get the right energies for hydrogen atoms. Finally, when you go and do the experiment, boom, you get the right photon energies experimentally with this model. Okay, it's basically the Drac model with radiative corrections. Okay.
But it's
And-
been flipped.
Right, there's isotope shifts I'm going to get into. Let's see. Right, okay, so I think that's a good place to end. We'll end this chapter with isotope shifts. What happens when you add different neutrons to the nucleus. And then we're going to move on to actually the transitions and get into multi-electron atoms. And I think we have maybe 2 more classes on this, and then we'll move on. Okay?
I got one of your